This is the Precalculus 2017 Senior ACP Study Guide. The ACP stands for Assessment of Course Performance, and we're going to have a final here in a couple of weeks, and we want to get ready for it. And this is kind of a comprehensive test we're going to have, and some of these review questions are going to be preparation for that. And so just kind of following along and having this study guide will really help you for your test in a couple weeks. One, the component form of vector v is 4, 5. What is the direction angle of this vector in standard position to the nearest 10th of a degree? And just to kind of see what that looks like. If we have a coordinate plane like this, an xy coordinate plane, and we go over, this vector is represented by going 4 units to the right, 4 to the right, and 5 up, 3, 4, 5. And so you have this point right here, and the vector is graphically represented as an arrow here, and so that's going to be it. What we have is a triangle we can form, and there's an angle from the right. Angle in standard form, in standard position, has to do with from the right, what is the angle that this thing is rotated up. And so on the right we have 5, and this would be the opposite side of that angle, and down below we have 4 equals the adjacent side of the angle. And so we can say that tangent theta is equal to opposite over adjacent, or the number 5 over 4. And to isolate theta, we can take the inverse tangent of both sides of the equation, and so we get theta is equal to inverse tangent of the fraction 5 over 4. And now we can just go to our calculator, have a T-inspired CX calculator, press the trig button, and we have to make sure that we are in degrees mode since we're trying to find the angle in degrees. So we press the inverse tangent, and we're going to go to 5 over 4. Sometimes people will put the 4 over 5, adjacent or opposite. So the nearest 10th would be 51.3 degrees. So we go back here. So theta is approximately equal to 51.3 degrees. And then we can mark this here in our answering grid, 51.3. And then we don't have to put a plus sign, the kind of assumes plus, so we put 51, and then the decimal point, 3. I will tell you that on your actual test, most problems are going to be a multiple choice standard. If vector v is 4, -3 and vector u is -5, 6, what is vector w if w equals v minus u? And so you can write this a number of ways. If we're going to take v and subtract u, we're going to have vector v is 4, -3, and we're going to subtract from it vector u, which is going to be -5, 6. And vector w is going to be the subtraction of these two vectors. So what we have is 4 minus -5, which is 9, and then we have -3 minus 6, which will be -9. And so this will be our answer. We can find the magnitude of this vector also, but we're going to get a magnitude problem shortly here, and specifically problem 3. So problem 3 is a vector in standard unit vector form. is 3i minus 5j. Well, what is standard unit vector? Well, what it is, it's simply I is equal to the unit vector 1 comma 0, and j is equal to the standard unit vector 0 comma 1. And so therefore our vector in component form is going to be 3 comma negative 5. And for that, our magnitude is going to be equal to kind of a version of the Pythagorean theorem, a version of the distance formula. We can just set it up like this. And then we just put in our 3 here and our negative 5 over here. And so when we start to work that out, we have 3 squared, which is 9. And then we have negative 5 squared. And negative 5 squared is not negative 25, but positive 25. And so what we have is we have the square root of 9 plus 25, which is 34. And so do not put 34 up here. Okay, we need a decimalized version to put in our answer space, and to do that we're going to go and put square root of 34. I think we're going to the nearest tenth, or is it nearest hundredth? 5.83. So we come here, so it is nearest hundred, 5.83, and that's what we put up here, 5.83. And then we go ahead and bubble in appropriately. Here's our 5, decimal point, and then 83. Okay, there we go. Let's go on to problem 4. What is the component form of vector u, shown below both in terms of sine and cosine and in decimalized form of the nearest tenth? What we have here is similar to what we've looked at earlier, is we have a triangle, which is a reference angle, and we have this is our theta, just like problem 1, and our opposite side is we don't know yet. Our adjacent side is we don't know yet. But we know that this is our opposite side. This is our adjacent side. And the thing we need to remember is our cosine theta equals x, and r, or the radius sine theta, is equal to y. So therefore, we can write this vector in component form as r. Well, our magnitude is our radius, so we have 11 is our r, cosine 48 degrees. And then we have 11 sine 48 degrees. Okay, so that's our component vector in terms of sine and cosine. And then if we decimalize this to the nearest tenth, let's just go and do this. We have 11 times cosine, and make sure I get the angle right, 48 degrees. 48 degrees, we get to the nearest tenth will be 7.4. And then for our other thing, we're going to put 11 times sine 48 degrees. We get 8.17, which rounded nearest tenths could be 8.2. So we have 7.4, 8.2. So we go to our here. So x value 7.4 to the nearest tenth, and then 8.2 And then if we went and took the magnitude of these vectors, we would find them to be 11. Okay, as a check. Next, 5. Describe the graph of each of the following polar equations. And what we're going to do is we're going to graph the first one. I'm going to ask you to get your graphing calculator, T-CX, and graph all of these yourself and describe what they are. The first one I'm going to do is kind of show you how to get there. We have Control I, and we'll go to graph. And the first one we have is 3 secant theta. Well, that's going to be a trigonometric ratio. So to get to a polar equation, we go to Menu, 3, and then 5, which is polar. So we have 3 times the secant of theta, and to get theta we press this pi key, and we get a little submenu there. We go to the far right and press enter. So we get a vertical line at x equals 3. So that is our answer here. Go ahead and put that. We get a vertical line at x equals 3. And I will have you go ahead and do the other shapes by yourself so you can see for yourself what they are. I do want to go ahead and tell you what some of these shapes are that you'll see. There's one kind of shape you're going to see that looks like this. Okay, this kind of shape is called a cardioid. Do you know why that shape's called a cardioid? Shaped like a heart. And this thing can be sideways, upside down. There's another one I'm going to draw here, which kind of looks like this cardioid, but starts out like this, and we'll kind of loop around. And this one here below is called a limacon. And that's a C with a little squiggle underneath it, with an inner loop. And limacon is a antiquated terminology for snail. I don't know if they thought this kind of looks like a snail. And then there's also going to be a type of function that's called a rose function, a rose graph. And it's going to look something like this, or could. Now it could have, just trying to draw this more or less carefully here, and that's not so bad. Okay, so this is called a rose graph. And we say this one has 4 petals. So like the flower petals. So you can have any number of petals in a rose graph. So anyway, go through all these and just kind of list what they are, and it's really familiarity with 1, entering these things in the calculator, and 2, with some of these basic shapes: a cardioid, a limacon with an inner loop, a rose graph, and then you'll have a circle and lines as well. 6, for the parametric equation, x equals 2t minus 3 and y equals 1 over t, what is the rectangular form of the equation? The rectangular form is just going to be finding an equation in terms of x and y. All right, so what we're going to do is we're going to take this first equation, x equals 2t minus 3, and solve it for t. And do that, if we add 3 to both sides of the equation, we get x plus 3 is equal to 2t. Well, then if we divide by 2, we have t. T is equal to x plus 3 over 2. And it's this thing right here that we're going to place right here in place of this t in the y equation. And we do that, we get y equals 1 over x plus 3 over 2. Well, you might remember back from your 7th grade math that dividing by a fraction is the same as multiplying by a reciprocal. So instead of dividing 1 by x plus 3 over 2, we can multiply 1 by 2 over x plus 3. And when we perform that operation, we get y equals 2 over x plus 3. And you can graph this parametrically by going to, in your graph menu, 3, 4, I think, and graph these two equations and then see which one matches. It's going to be a multiple choice type situation on your test here in a couple weeks. Next, 7. The flight path of a baseball is given by the parametric equation x equals 125 cosine 23 degrees t and y equals 2.5 plus 125 sine 23 degrees t minus 16t squared. What's the maximum elevation of the ball? So how high will the ball hit the wall that's 310 feet away from home plate? And also, what is the time in seconds it takes for the ball to reach the outfield wall? So we have the answer places down below. We're going to bubble these in. So we're going to find a graph a parametric equation, and to do that we press Control I, and we get a graph page, and then we get the parametric equation by going menu, 3, 4, graph parametric, x equals 125 times cosine 23, and we have to put the degree symbol here or else we will be messed up, and times t, and for the y equation we're going to put 2.5, and that's the elevation off the ground that baseball hitting starts, times 125 times sine of 23 degrees, and we get our degree symbol again, and we put times t, and we subtract 16t squared, and minus 16t squared has to do with position change due to the effect of gravity in feet per second squared. Anyway, I'm going to change the t step to 0.031. Why 0.031? That's going to be 100th of pi. Pi is roughly 3.14, and 100th of that is going to be 0.031 somehow. It works pretty well. So if we just press enter, we see the baseball hit at 2.5 feet, but we don't see the whole thing. So I'm going to change the menu. I go to menu and show to window zoom, window settings, and we're going to go from x equals 0, and our fence is 330 feet away, so I'm going to put 310 feet away. I'm going to put 330 just to make sure we have enough room. And then for tab, I'm going to go up to, I think, y max is 60 feet. I think that should get it. Then we go to OK, and we see a flight path of a ball. I think this should do the job. And then we can just kind of pick things out as we go. We can go to trace, press 5, trace, graph trace, and we're trying to find one of the things I believe is maximum height of the ball. So I'm looking, maximum height is this second number here in the coordinate pair, and right now 36.6, and we're going up 37.7, 38.1, 39.1, looks like it's leveling off 39.4, 39.7, 39.8, 39.8. So 39.8 is as close as we get. And we go to our answer choice here. It says maximum elevation of all. So we say 39.8, And it says, what does it say? Both answers to the nearest foot. So that would be approximately 40 feet. And so we're going to just put in 40 here. And we bubble that in. Here we have the 4 and the 0. Okay, next we'll find out how high the ball will hit the wall that is 310 feet away. So we go back to our calculator and continue. And we want to find 310 feet. We're looking at this x value here, which is now 231, to be 310, or as close to 310 as possible. So we go over here and get them close. 304, 307, 311. So between 307, 311, 310 hits the ball. So at 311, we're 17.7, and at 307, we're 18.8. So my best estimate is going to be probably closer to 17 than 18. So we'll say about 18 feet high. So we'll put approximately 18 feet. And so we put in the number 18, bubble that in, 1, 8, and finally, what is time in seconds it takes for the ball to reach the outfield wall. So we go here, and we read this 2.7, okay, that's 2.67, 2.7, 2.73, so it looks like 2.7 is going to be about as close as we can get, as in 2.7 seconds. So we'll say approximately 2.7 seconds. So we'll put in 2.7. So we put in 2 here, decimal point, 7. There we go. Okay, let's go ahead to problem number 8. The angle of elevation from ground level to top of a building is 58 degrees. The vertex of the angle is 250 feet from the base of the building. What is the height of the building to the nearest foot? I think it might be helpful to make a little drawing here. If we draw a horizontal line which represents ground level, and then we can go ahead and construct a building. And there's a building, too pretty. But we have an angle from ground level to the top of that building, which is 58 degrees. And we have also this distance from that line of sight, which is to the base of the building, which is 250 feet. All right, so in the vocabulary of trigonometry, we would call this height of the building here, we call this height our opposite. Okay, that's our opposite side. This distance 250 feet below here is going to be called our adjacent side. So our tangent of theta equals opposite over adjacent. Well, it's opposite over adjacent. So the tangent of our angle, which is 58 degrees, is equal to our opposite side, which is our unknown h, and our known adjacent is 250 feet. So solving for h, cross multiplying 250, we have h is equal to 250 times the tangent of 58 degrees. Now, I know some of you might want to use your numerical solve at this level right here. We can go to our calculator and get another page. And we have 250 times tangent of 58 degrees. And we see that our calculator is in degrees mode, so we get 400.084. I think we're going to the nearest foot, so we say h is about 400 feet. So marking that in our space here, we can put 400. And so we put in 400. Okay, so that's problem number 8. Problem number 9, for the triangle shown, what are the 6 trigonometric ratios? Well, basically, the 6 trigonometric ratios are going to be sine theta. Okay, we have reciprocal of sine theta, which is cosecant theta. We have cosine theta. We have reciprocal of cosine, which is secant theta. We have tangent theta, which we abbreviate TAN. And we have reciprocal of tangent, which is cotangent, abbreviated COT. And to find out what they are, right now we have our theta, and this 10 over here at the bottom is an adjacent side. The longest side over here at the top is our hypotenuse, which we abbreviate HYP, and our opposite, which is the opposite side from the angle, is what we do not know yet. We can find that using the Pythagorean theorem, a squared plus b squared equals c squared. And so a squared, we'll say 10 equals a. So we have 10 squared plus b squared equals our longest side squared, which is 12 squared. So if we subtract 10 squared from both sides of this equation, we have b squared is equal to 12 squared, which is 144, minus 10 squared, which is 100. And so we have b squared equals 44, and taking the square root of both sides, we have b is going to be equal to plus or minus square root of 44, but because we're talking about distance here, we only concern ourselves with the positive value. So our opposite side here is square root of 44. And I'm going to move these things over a little bit because we're going to kind of run into a hard time moving. There we go. Just to leave ourselves a little room. Okay, so our sine is going to be equal to our opposite, which is square root of 44, over our hypotenuse, which is 12, and the okay, 12, there we go. And our reciprocal is going to be cosecant, so we're going to have 12 over square root of 44. Our cosine is going to be our adjacent over hypotenuse, so we're going to have 10 over 12. And yeah, that'll simplify if you want to, in simplest form, to 5 over 6. But our secant is our reciprocal of cosine, so we have 12 over 10. Our tangent is our opposite, which is square root of 44, over our adjacent side, which is 10. And our cotangent is going to be just the reciprocal of that tangent, which is going to be 10 over square root of 44. So these are going to be all of our answers here. Okay. Next, let's go on to problem 10. The polar coordinate pair is 4, 150 degrees. What is the rectangular coordinate pair in the exact radical form and in decimalized form? Well, we have a basic equation here. We have our cosine theta equals x, and our sine is 1. So we have in a coordinate pair, this first value here is going to be our radius. So we're going to say x is equal to 4, which is our radius, times the cosine of 150 degrees. Well, I just happen to know that the cosine of 150 degrees is going to be equal to negative square root of 3 over 2. So therefore, x is going to be equal to 4 times negative square root of 3 over 2. And 4 divided by 2 simplifies to 2, so we're going to have negative 2 square root of 3. So in our coordinate pair, we would write that as negative 2, comma, excuse me, we write that as negative 2 square root of 3. And now we're going to get our y value. So y is equal to 4 sine of 120 degrees, 150 degrees, 150 degrees. And I happen to know that sine of 150 degrees is equal to 1/2. So y is equal to 4 times 1/2. And 1/2 of 4 is equal to 2. So our y-coordinate in rectangular form is 2. And then in decimalized form, we're just going to have to work this negative 2 square root of 3 out. Or one thing we can do equally as well is we can just put, it's in the calculator, 4 times cosine 150 degrees. So we go here and we put in 4 times cosine 150 degrees, and we are in degrees, so we get negative 3.46. And then for the y value, we put in 4 times sine of 150 degrees, and we get 2, just like we had earlier. So negative 3.46 comma 2. So this first pair is in exact radical form. This second pair is in decimalized form to the nearest hundredth place. And just try the same thing using the equation here. The x equals r cosine theta, y equals r sine theta for this second polar coordinate pair to get some exercise, just practicing that. Okay, next problem here, 11. For an angular standard position of 150 degrees, what is the measure of its reference angle? Well, basically what we have here is we talk about standard position. We're talking about an angle rotated from the right. And so our initial side is over here where this red arrow is being drawn. And then 150 degrees is going to be over here, which I'm now drawing, which is going to be the terminal side of the angle. So 150 degrees is going to be this rotation here, counterclockwise. And our reference angle is the closest angle to the x-axis. And so I'll call this angle alpha here. It's going to be equal to 180 degrees. So we'll say alpha equals 180 degrees. And we're going to subtract the 150 degrees. So we're going to get 30 degrees being our reference angle for this one. Okay, now for an angle standard position of 335 degrees, what is the measure of its reference angle? Well, in this case, 335 degrees, I'm going to draw this one in purple here. We're starting here, and 335 degrees is going to be out to about where I'm now drawing this ray. And so the rotation is going to be like this. Okay, that's going to be 335 degrees. Well, what we want to find is this angle right here between the 335 degree terminal side and the x-axis, the nearest one. And to find that, we're going to have to subtract that from 360. And so you have to decide what to subtract. You have to do the subtraction that gives you a positive number. So our alpha in this case is going to be 360 degrees minus 335 degrees, and it's 25 degrees. So in quadrant 4, we have to subtract from 360 degrees. And in quadrant 2, we have to subtract from 180 degrees. And this last one here, 255 degrees, is in, okay, I'm drawing this to the right in blue. 255 degrees is going to be right here where I'm drawing this blue terminal side here. And what that's going to look like is this. Okay, that's 255 degrees. And what we have to do for that is we have our alpha. We're looking for this angle between the x-axis here. It's going to be this 255 degrees minus 180 degrees. And that's going to be 75 degrees. So for this, we have to, in quadrant 3, subtract 180 degrees from that. So slightly different. Now in quadrant 1, the reference angle and the standard position angle will be the same thing. Okay, problem 12. An angle that measures 144 degrees is how many radians in measure? Answer in terms of pi and also in the decimalized version of the nearest tenth using the grid provided. Well, what we have is 144 degrees, and to convert into radians, we're going to multiply by pi radians over 180 degrees. And so we have degrees over degrees cancel, and what we're going to have left is, in terms of pi, 144 over 180 pi radians. And so in our calculator, we can go to find that simplified version of 144 over 180, and we get the simplified version 4/5. So our answer for this is going to be 4 pi over 5, and the units are going to be radians. And sometimes if you just have it in terms of pi, that's really kind of assumes radians. I put RID just to be sure. Now, decimalized version, we just have to find out what that is when we put this in the calculator. So we're going to take we're going to take 4 times pi over 5 and see what we get. So about 2.51. So we go here. So 2.51, and it says to the nearest tenth. So that would be the first decimal place. We'll say 2.5 radians. So in our grid we put in 2.5. So we bubble in that 2, and then we have 0.5. Again, in your test, you're going to have mostly multiple choice. Okay, 13. For the triangle ABC shown below, what is the measure of side B to the nearest tenth? So we don't have right angles, it looks like. But what we look for, if we see a known side opposite a known angle, in this case we have the side 15 opposite the angle 48 degrees, we can use the law of sines, which is sine angle A over A equals sine of angle B over side B equals the sine of angle C over side C. And by convention, we'll just make the angles the big letters and the sides opposite them the little letters. And so we have a ratio, which is 15 over the sine of 48 degrees. And we know it's going to be equal to this unknown side B, the ratio of side B to the sine of angle B, which is 80 degrees. And so we can now just enter this equation in our calculator. And so to do that, I'm use numerical solve, algebra 1. And so we get a fraction here, B over sine of 80 degrees. And this is going to be equal to the ratio of equal sign. We have 15 over the sine of, I think is it 48 degrees? Yeah, 48 degrees, I was right. So 48 degrees, and then we go over here to the right and put in our comma B, and we get 19.9. I think it's the nearest 10, 9.89, 19.9. So we'll say B is approximately equal to 19.9. So we write this up here, 19.9. And bubble this in. We put in the 1. Decimal, actually not decimal point yet, 19. Then 0.9. Okay, 14. For the triangle PQR shown, what is the measure of side Q to the nearest tenth? Well, this is going to be a law of cosines. How can we tell? Because we have side, angle, side. A known side, angle, side. That's a law of cosines application. And we can't use law of sines because we don't have any known angle opposite a known side to really use a ratio for the sine. And so law of cosines is going to be c squared equals a squared plus b squared minus 2ab cosine c. And in this case, we're going to say a is 16 and b is 21. And so we're just going to write this as c squared equals 16 squared plus 21 squared minus 2 times 16 times 21 times cosine of our angle, which is 112 degrees. And so like we did in problem 13, we're going to use numerical solve, menu 3, 1, and we have c squared equals a squared, which is 16 squared, plus b squared, which is 21 squared, minus 2 times a, which is 16, times b, which is 21, times the cosine of c, and cosine of angle c is 112 degrees. And then we go to press here to the right, comma, c, what we're solving for. We get to the nearest tenth, I believe that's 30.8. So we go to this, we say c is 30.8 rounded to the nearest tenth. So we put in 30.8. So we go here and put in 3, 0.8. Okay, that's good. Next, problem 15. Art puts up a basketball shot according to the parametric equation x equals 28 cosine 6 degrees t, y equals 8 plus 28 sine 6 degrees t minus 60 t squared, where x and y are feet, and t is the number of seconds. What's the maximum elevation of the basketball? And there's 10th. Mark your answer using the grid provided. What I did for this one is I pre-entered this equation here, and I'm going to go get a parametric equation, 3, 4 parametric, and I'm going to go up here, and this is it, pre-entered right here, the x and the y equations. I'm going to go down here and change that to 100th of pi, which is 0.031. And when I graph this, I don't see it initially, but I have to change the window. So if we set the window zoom, go to window settings, we're going to go from x minimum to 0 to maximum of 30 feet for a 30-foot shot, and then y minimum will leave the same, and then y maximum we'll put at 25, as in 25 feet. And then we press OK, and we see the arc of a basketball shot. So we're trying to find the maximum elevation, and so to do that we go to Menu, Trace, which is 5, Graph Trace, and here we have right now at 8.88 feet, and we're going to arrow to the left, and so we're going and we're looking for a maximum elevation. So we get to 16.5, 16.7, 16.9, 17, 17.1, 17.2. So it looks like 17.2 feet is the highest I see, so approximately 17.2. And it says to the nearest tenth, so that's going to work out. We'll just put in 17.2. So put in 1, 7.2. So that would be 15, 16. What's the magnitude of vector W if W equals 5, -4 to the nearest tenth? Well, our magnitude for this, and we did this earlier, I think in problem 3, is just to take this 5 here, square it, plus -4 here. So we're just taking this 5, just putting it right in here. We're taking this -4, putting it right in here. And what we get is 5 squared is going to be 25, and -4 squared is 16. So we're going to get the square root of 41. But we cannot put the 41, square root of 41 up here. So we're going to go to our calculator, and we need the nearest tenth. So get a calculator, and square root of 41, and that looks like the nearest tenth, 6.4. So 6.4 we'll say. So we go up here and we put in 6.4. Now we can put these answers anywhere in the grid we want to, as long as the numbers consecutively are correct. So 6.4. Okay, problem 17. The graph of the polar equation r equals 3 cosine 2 theta forms a rose. How many petals does a rose have? So we just have to enter that in our calculator. And to do that, we're going to get a page, and we're going to add graph, and we're going to go to menu, 3, 5, which is polar, and we're going to put in 3 cosine, and we're going to put in 2 theta, and we're going to get the theta from right here, and we make sure everything's entered correctly, press enter. We get 4, we count 4 petals in our rose graph there. So I'm going to put 4 petals. And the number of petals is our answer, so we're just going to put here 4 and bubble that in. That's it. Very simple. Problem 18. Plot the polar coordinate pair, -4, 110 degrees, using the polar coordinate graph paper marked below. Mark the coordinate pair, -4, 110 degrees, clearly next to the plotted point. So first thing we'll look for is this angle, 110 degrees. And so we have this marked pretty well. We have 90 degrees, so 110 degrees is going to be this right up here, where I'm dashed lining here in blue. So that's our 110 degree mark on our polar graph paper. But we have a radius of -4, so we can't just go up here to 4 and mark it right here. We have the radius, this is shown here, 2, 4, and 6. So we have to go the opposite direction down here to get -4. And so it's going to be this point right here. And to mark clearly, we're going to put next to it the coordinate pair, and these instructions, -4, 110 degrees. So on this question here, you could be given a positive or a negative radius. In this case, a negative. So just be aware of that. Okay, problem 19, the last problem. What's the direction and standard angle position of vector z if z equals -6, -7 to the nearest tenth of a degree? Well, first of all, we have to understand where we are, because if we just draw a little xy coordinate plane, we'll see that -6, -7, when we go with -6 to the left, 1, 2, 3, 4, 5, 6, and -7, 1, 2, 3, 4, 5, 6, 7. So we're talking about this point right here that this vector comes to from the origin, and it's going to be this value right here, which is at this point -6, -7. And what that's going to give us is a vertical component here, opposite side. So our opposite equals -7, and our adjacent side here is equal to -6. And so we're going to get our tangent theta is going to be equal to the ratio of our opposite, which is -7, to our adjacent, which is -6. But in standard angle position from quadrant 3, we have to add 180 degrees. So we take our theta in standard position is going to be equal to our inverse tangent of -7 over -6 plus 180 degrees. Now you got to be careful in this question, because you could be given a coordinate pair in either quadrants 2, 3, or 4, possibly, and for that you'd have to know whether to add 180 or 360. In quadrants 2 and 3 you add 180, in quadrant 4 you add 360 degrees. So we just go to our calculator and we put in a page here, and we put an inverse tangent of, now we could put in 7 over 6 instead of negative 7 over 6 because we know that the negatives cancel each other. But to that, we add 180 degrees. And if we're correct, we're going to see an answer between 180 and 270 degrees. That's going to be 229.399. So the nearest tenth, I think that's 229.4 degrees. So we put it up here, 229.4. So we just bubble that in to 29.4. Now I believe what we've gone over today is going to be everything that's on this test. So if you know all this stuff well and use your study guide, you're going to get a good grade on this. So I encourage you to do that, do your best, and as always, good luck and thanks for viewing.